Bignall and myself will be talking about some of the binary power plants we have in New Zealand. So a brief outline of what we'll be discussing. I'll look generally at the situation in New Zealand. I'll discuss the binary power plant that's at the Ngāpumariki geothermal field. Bignall will talk about the binary plant in Napa, and then we'll follow that up with a discussion. So there are a number of binary power plants operating in New Zealand. Fields with plants are notified. Then we have three other fields where binary plants are operating in conjunction with a steam turbine. Kawa, Wairaki, looking briefly at a couple of examples. So the Mokai geothermal field is operated. It's been developed by a local landowner. They have a combined cycle technology. They've developed the project in stages. The initial stage was a 60 megawatt development, and then there has been an expansion, and currently they're operating at about 110 megawatts. Given the nature of the reservoir, probably the best option for generation of electricity may have been a steam turbine, but because of the need to stage the project, the decision was made to use binary plants. That choice has added to some of the complexity in operating the reservoir, but the modular design has had benefits. There's been some pluses and minuses from this arrangement, but overall I think it's been a reasonable choice for the development of that field. The second example of a binary plant that we have is at the field Kohara. This is a 25 megawatt development, which was originally planned for a specific industrial use. However, the situation changed, and it was decided that the plant would be used to generate electricity for the national grid. At that size of development, a binary plant was the best option. Once again, in terms of the reservoir, it may not have been the best option. Perhaps a steam turbine could have been better. And at this stage, there are plans for a 250 megawatt development of that field using a steam turbine. But as was discussed earlier in the day, some of those plans have been stalled due to the low demand for electricity. So here we have a couple of examples of binary plants that are in use that have come about more from the arrangement of the project and the necessity, the planning of the project, rather than related to the aspects of the reservoir. We also have a number of fields where we have binary plants operating alongside traditional steam turbines. As was mentioned earlier this morning at Wairaki, there is a small-scale binary plant that is extracting heat from some of the separated brine. At Kaurau, Kaurau's a complex situation. Over the years, some of the steam has been used for direct use, and now quite a bit of it is being used for electricity generation through a steam turbine, but there have been 3 small-scale units developed by local operators. They are small-scale, they're 14 megawatts in total, and again, the optimal choice for that has been binary plants for those. Again, this is related to the logistics of the project impacts rather than the reservoir conditions themselves. Burnell is another example. This was a planned stage development with a small first stage, a 35 megawatt binary plant was decided that was the most economic and suitable arrangement for that first stage. Since then, 140 megawatt steam turbine has been added to that reservoir. So these are some examples where binary plants are in use, but again, the choice of binary plant for these developments has been related to project conditions rather than reservoir conditions. The first example, I guess, that we have of a project, the first example we will talk about of an example of a project where the choice of a binary plant relates to the specifics of the reservoir is Ngātamariki. Ngātamariki is the most recent power station, I think it's the most recent development in New Zealand. Exploration for this power station occurred between 2004 and 2009. It is a high temperature resource with measured temperatures of more than 285 degrees. It's really dominated. There is an extensive cap, and through that cap we have a very local area where there's a connection to the surface. I'll say some more about that in a minute. Just reminding you again where Ngātamariki is, so it's that field there, surrounding the Wairaki, Wairakawa, and Ohaki fields. This is a map of the Ngātamariki resource. The green shaded area is the resource boundary that's come from the NT analysis. There were originally 4 wells that were drilled in the 1980s. EN1, EN2, EN3, and EN4. Then when the exploration phase started in about 2004, new wells EN5, 6, and 7 were drilled. These are reservoir temperatures for some of the main wells in the interior of the reservoir. So we can see a consistent temperature in the reservoir, about 280 degrees. We have this characteristic where EN7, which is this more southern of these 3 wells, so we're looking at temperatures at EN2, 3, and 7. And EN7 is the more southern of those wells. And EN7 has a conductive profile up through the cap. Whereas EN2 and EN3 are showing these shallow inversions. And these have been interpreted as the outflow from the geothermal field into the shallow groundwater is occurring somewhere in the vicinity of these wells. And this gives rise to our conceptual model for the reservoir. So we have a deep upflow somewhere. This shaded area, grey shaded area that we see here is the low resistivity clay cap that's been identified from the geophysics. And we have this updoming in the cap and a connection through to the shallow groundwater. So we have a regional groundwater flow from south to north, and that picks up the geothermal fluid as it comes up into the shallower parts of the area. So as part of the exploration phase of this work, we undertook some reservoir modelling. This is the grid that we used for the model. We, as I mentioned earlier, we worked through the same process, matching the natural state temperatures. These are matched some of the natural state temperatures. But in this phase of the work, but for this reservoir, we had no production history. The reservoir was not producing, so we did not have a production history to match it. We had a little bit of data. We had a pressure interference test that was undertaken over a period of about 2 weeks. We used that to calibrate some of the reservoir permeabilities. Based on that reservoir model, we ran a number of scenarios of how the reservoir could be developed. One of the important aspects that we were looking at was the flow from the reservoir to the groundwater. So in the natural state, we're seeing something like 100 kilograms per second of flow out of the reservoir. If we run a scenario with a conventional steam turbine, where we have perhaps something like 75% injection, then we find that outflow reverses to a downflow. So now we have colder groundwater coming back into the reservoir. On the other hand, if we run with 100% injection, then we find that outflow is maintained. So we no longer have a situation where we generate a downflow into the reservoir. Based on these predictions, the decision was made to move to a design for the 100% injection. And this had the impact of helping to maintain reservoir temperatures, so to minimise the impact of colder fluid coming into the reservoir, and also minimise any impact on the environment. There are some hot springs related to this reservoir, so maintaining 100% injection means you have a very small pressure decline and minimal impact on those surface features. Based on that decision for 100% injection, really the only viable technology was a binary plant. However, it did have an impact on the project economics. There is considerably more competition around in terms of steam turbines, and the costs are somewhat more competitive. But after quite a lot of work, it turned out that the economics were viable over the lifespan of this project. So we've now ended up with a project with a 100 megawatt power station. It's the largest all binary single site plant. It's using 4 25 megawatt format energy converters. There are 3 deep producing wells, and 100% of the produced fluid is re-injected back into the reservoir. And the injection wells are placed around the periphery of the field to reduce the impact of cooling on production wells. We have found that there's been some thermal stimulation of those injection wells, and the field has been operating since 2013 with more than 96% availability. I'll now turn over to Simon to talk about place for us. This morning we heard from Chris Colby about some of the resource characteristics of the system. So now we look at the development history. This is an example of stage development. It's important to look at this, the history of the development, because it's a project that was developed through a community trust. And in New Zealand, the buy-in, the communication and engagement with communities are a key aspect of the success of the project. We won't go into detail here, because that is a subject of Andrew Blair's presentation shortly. But it is a key component of business. The project developed in stages. Initially, the 10 megawatt development, followed by expansion to 15 megawatts. And we recently, GNS is working with the developer at Burnell, have supported their increased take from the geothermal field. So they have recently been awarded consents for a further 15 megawatt expansion. As we've heard, the resource is a lower entropy resource than the systems of the Tapu zone. So Napa is resource temperature around 250 degrees. And the stage
concerns, just as with many developments here in Japan, was the potential effects on the hot springs. We've seen some examples that this probably presented earlier, some pictures of the hot springs. And similarly to Natariki and other places, reservoir modeling has shown that the springs and the surface features are sensitive to pressure change. And so at NAFA, as elsewhere, the option was preferred to look at 100% injection as a to mitigate the possible effects on the surface features. Part of that process was to add supplementary injection because there were some losses to the injection plan. The historical declines, they were small, but there was the ongoing need to avoid any future decreases in pressure because of concerns that the hot springs might be impacted. So a trial was conducted, and that demonstrated that pressure could be changed through the supplementary injection process. As a consequence, as part of the consent process in New Zealand, the developer was able to demonstrate to the regional authorities that the impacts on surface features, impacts of concern to the local communities could be mitigated. And with that understanding of the source, the pressure was granted to proceed to the next stage of the development. So that stage commenced in 2008, and as a consequence of good science, good modeling, good communication with the local community, ongoing monitoring, it was able to demonstrate that there was no clear impact on the surface features. Certainly, changes do occur naturally in a large geothermal systems, but that could be very easily explained through natural variation. As a consequence, after 30 years of operation and new information about the reservoir, new information about how the reservoir would perform, the decision was made by the developer to consider expansion to a total of 75 megawatts, and that's the situation that we are in today, that those consents have been made. As part of the consent process in New Zealand, however, there are still some obligations that the regional authorities who sign consents can impose on developers. And in the case of NAFA, that is exactly what happened. So the conditions imposed on development were that the operators must maintain reservoir pressures in the field at 2,000 levels, and that they should have no effect on surface characteristics of the springs. So very raising the bar quite high, but the expectations on the developers at NAFA, but also at other fields in New Zealand, to maintain and preserve surface features, or to find some process to protect those features if effects are being noticed. So, in summary, for the use of binary plants in New Zealand, the major use is for small-scale or stage developments. The project economics are obviously very important, but the use of binary plants adds flexibility to the developments because binary plants can be modular and we can actually build up the development over a period of time as you observe change in the reservoir. It can also be driven by the need to minimize the impacts on the reservoir of the surface features, as we can see at NAFA and on the basis through 100% injection. It's very pleasing that the projects have been successful, and these have resulted in expansions from initial stages. Natariki, Rokai, NAFA, Tahara, Rodikawa expansion, Rodikawa expansion, and additional plants being constructed. good modelling, not overdeveloping the resources early on, but pitching things at the level and then building up from there. So with these stage developments, the initial stages can be advanced with small to medium-sized binary plants, assess the reservoir performance, add expansion, and reduce risk. As John Burnell also pointed out, the use of binary plants can complement a steam turbine, and the example that we demonstrated is a project where we can utilize heat and separated geothermal brine. Does have